Good afternoon, everyone. My name is Terofadzo Sinona. Today, I'll be doing this talk with Khomodzo Ngwebe. We are both a final year computer science student at the Tshwane University of Technology, and we are currently CSIR in service trainees. Today, we'll be taking you guys through the CTIP decentralization. CTIP, the abbreviation CTIP stands for Cyber Threat Intelligence Exchange Platform. So it is a platform that collects and shares security-related data. It uses intelligence from various sources for cyber threat monitoring and detection. Now, the aim of CTIP is to offer stakeholders with relevant indicators of compromise, strategies that they can use should they experience the kind of threat that other stakeholders have encountered, possible targets that they might encounter, and the threat actors that are actually threats to their organization. It also serves as a centralized nodal point. Now, this is a visual representation of the CTIP architecture. So, for example, you will have a CTIP, a stakeholder that encountered a threat. Then they will publish the threat to the CTIP, to the central CTIP, where the threat has been processed and filtered. And then now it will be distributed to different stakeholders. Now, the distribution also depends on the traffic light protocol that they would have selected to share to different stakeholders. The technologies that are used on CTIP as it's React.js, Django, and MongoDB. MongoDB is used for storing our data. Django is for the back end, and React.js it's used for the front end. It's that it had limited scalability, meaning that it can only take limited amount of requests. So should there be should the system experience peak period, that means it won't perform very well. So that means it also had one point of failure. So should the server go down, it means that the system won't operate at all, which makes it unreliable. So the solution that we decided to come up with on the CTIP system, we decided to decentralize the system. As you can see on the picture below, we have one client that is able to send requests to multiple, a cluster of servers. One might ask, why did we actually decide to decentralize the system? Decentralization helped us in terms of creating several servers. We were also able to create a cluster of servers running together to perform one task. For example, right now we replicated the servers, and also we were able to create a cluster of database servers that can operate together should there be a failover. It also helps us in terms of better performance on our system, and it also helps in intelligent fault tolerance policies, meaning that should you be on the system and one of our servers that you connected to, it shuts down, it means that your request will now be deflected to another server, but you won't be able to notice that. It also has a high availability and scalability with the servers that we have implemented on the system. So the approach that we took, we firstly replicated the existing servers, the existing server, and then we also introduced a load balancer to ensure that our servers communicate, and also we replicate the database servers.
With replicating the server, we take the exact copy of the existing machine, then create a new server based on the existing one. So as you can see on this picture, we have a 3 servers that are running on the different locations. So the server that's running on location 1 is a original server. Then the one that's running on location 2 and 3, they are copy of the server that is running on location 1. So this type of replication is called a peer-to-peer replication. So with peer-to-peer replication, these servers are not able to communicate. So to make them communicate, we introduced a load balancer and database replica. So one might ask, what is a load balancer? Load balancer is a software that is used to distribute incoming network across the servers. So you can take a load balancer as a middleman that is receiving requests and distributing it to the servers. So this picture demonstrates how does a load balancer work. So we have a client sending the request. So load balancer will receive and provide a better experience for clients. So as I mentioned on the last slide, that a load balance algorithm that we use is round robin algorithm. So round robin algorithm operate in an orderly manner. So this picture demonstrates how does a round robin algorithm work. So we have two servers and a 6 client. So let's say the client number one send the request. So run algorithm will be instructed to take that request and send it to server number one. So when the client number two send the request, so the load balancer will be instructed to send the request to server number two. So no, the server number two is our last server. So when the client number three send the request, load balancer will be instructed to send the server number three to server number one, and this process will repeat over and over again. So the load balancer software that we use is HA proxy. So HA proxy stands for high available proxy. So one might ask, why did you use a HA proxy? HA proxy improved the performance of the system. During the maintenance, there's no downtime, and it also gives access to integrate with server monitoring dashboard. So CTIP improve the system, high availability of our system, and it also give it also load the request. It also balance the load. It also balance the request to the servers, and it also proxies for reverse HTTP. So this picture demonstrates how does the load balancer proxies for HTTP. So we have a client sending the request to the server. So the HTTP will receive the request. HA proxy will receive the request, then the request will be sent to one of our server, depending on the algorithm that is used. So the server will receive the request and generate the response, then the response will be sent back to HA proxy. So HA proxy will give the response to a client. So this is an example of a dashboard that HA proxy comes with. So this demonstrate we have two servers, all of them they are up. So it also show the total request, how long does the server is down, then yeah. So know that we load balance our servers and we replicated our servers and load balance our servers. So to make sure that our servers are on the safe state, we replicate the database.
Okay. Now that we have replicated our servers and we also introduced a load balancer to ensure that our 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 our, our database is on the same state, we used what we call replica sets. Replica sets are MongoDB instances. They ensure that our database is it's on the same state in all the servers. Now, how does the replica set work? Replica set works in terms of members. So you will have a primary member and then with the two secondary members. Basically, the primary member is responsible for reading and writing data. The secondary members are only responsible for reading and replicating data. So should there be a failover, your secondaries will therefore make an elimination between the two. I'll get into that later on. But then how do these members communicate? These members communicate in terms of heartbeats after every 2 seconds. So if a heartbeat does not reply within 2 seconds, within 10 seconds, the members mark that that member as inaccessible. And then if the primary is inaccessible in this case, because it's responsible for reading and writing data, therefore now an eligible secondary selects itself as the primary for reading and writing data. So now, how does it become eligible? It becomes eligible in terms of priorities. The one that has the highest priority, it's the one that gets to be selected to be your primary. Therefore, it's going to be responsible for reading and writing data. So if the cluster is now done with eliminating the secondary that is responsible for writing and reading data, your cluster closes and then operations continue as normal. This is a picture of when there is a failover with the primary. There's going to be a heartbeat communication between your secondaries, and a new primary will be elected based on the priority that you would have selected. So now with CT being decentralized and making sure that we have our servers and data is equally distributed, we have what we have analyzed is that the system it has high performance, and then it also it's reliable, and also again it is yeah, we can rely on it, and then it also it's able to render the services to the client should there be any point of failure, or should we want to maintain.
Unfortunately, our next speaker couldn't make it due to illness, so we have to move to Simran Rathilal. Sorry, I'm struggling with the names today. Automatic detection of illegitimate traffic, the case for the South African National Research and Education Network. Thank you very much.
Okay, hi. My name is Simran Rathilal. I'm doing automatic detection of illegitimate traffic, specifically within the Sunray network. So just an outline of the presentation. I'm going to do an introduction, speak about the problem that we are currently facing, and then go on to the main idea about detection and my conclusion. Yes, so the introduction. Cybercrimes are increasing in both frequency and severity. Network forensics, which is used in this project, is the investigation of network traffic in order to acquire evidence. The South African National Research Network, SANREN specifically, contains a significant amount of data that might include cyber attack evidence. SANREN currently does not implement a method for distinguishing fake from regular network traffic. This is problematic since illegitimate network traffic can be malicious. So my project specifically aimed to test the accuracy of the k-means clustering algorithm to determine which traffic is false within the Sunren network. By using feature selection, we may be able to generate a model with a higher classification rate. This is intended to increase the efficiency and accuracy of detecting fraudulent network traffic. So the problem that we are facing at the moment, according to a 2007 study, hackers used to attack computers and networks at a pace of 1 per 39 seconds. However, according to the Internet Crime Complaint Center report for 2020, 456,177 incidents were recorded, which equates to one successful intrusion attempt every 1.12 seconds. This does not include attempted or unreported attacks. Most of the information needed to combat these attacks is easily available to investigators. However, certain unidentified data is retained deep inside network traffic that may be beneficial in cybercrime detection and impact reduction. Capturing network traffic is difficult due to a variety of factors, legitimate data. So my main experiments at the moment, I use two data sets. Firstly, the Sanren dataset, which was given to me by Sanren themselves. It is important to note that Sanren dataset is unlabeled, and labeling was attempted according to general web traffic rules, but this was unsuccessful as only one rule, namely duration, could be determined, and it would be inaccurate to label the entire dataset based on just one attribute. The second dataset was the KDD CUP 1999 data. This dataset was already labeled with normal and then different attacks, but for the purpose of this study, all the attacks were labeled as false. I specifically used Weka, which is a common tool readily available to implement various machine learning algorithms. It allows for the datasets to be examined using a built-in visualization tool. So for my main dataset, 20,000 samples were taken from Sanren and 20,000 from the KDD dataset. The data was shuffled so that no clear groups can exist between the datasets. It was shown that there are only 4 common features between these two datasets: duration, protocol, services, and flags. However, upon further inspection, it was noted that the flags in both datasets do not match, and this feature was therefore dropped. It was also noted that bytes in the Sanren dataset could be calculated by summing source bytes and destination bytes in the KDD dataset. So feature extraction was done using a Python script, and only the attributes that were the same in both datasets were taken. Since only some of the data is labeled, semi-supervised clustering was used in the form of the simple k-means algorithm. A case size of 2 was used since the algorithm is attempting to cluster between two classes, normal or fake traffic. Euclidean distance was used as the distance function with a random initialization method, 500 maximum iterations, and a seed of 10. So the percentage split mode in Weka was used to split the data into 75% training set and 25% test set. This resulted in 70% of the data being clustered as normal and 30% clustered as fake, with 2.73 seconds taken to build the model. The classes to clusters evaluation was used, which resulted in 46% of the data being clustered as normal and 54% clustered as fake, with 8.76 seconds taken to build the model. Papers which also made use of k-means clustering. The first paper published in 2007, the unsupervised k-means algorithm was tested on multiple network traffic datasets to analyze its effectiveness and performance. According to their experimental findings, the algorithm achieved an overall accuracy of up to 80%. Another study compared k-means and dbScan to a previously used autoclass algorithm to evaluate the accuracy with regards to network traffic classification. Specifically with k-means, the overall accuracy of the two datasets which were used in experiments was 79% and 84% respectively. The results of both of these studies correspond with the experiment in this paper, achieving 83.24%, which is approximately 80%. In conclusion, the accuracy of the k-means algorithm is tested as a way of distinguishing between real and illegitimate network traffic within the Sanren network. This would essentially identify a viable technique for detecting fraudulent traffic, since some illegitimate traffic is potentially malicious. Experimental results show that the k-means algorithm is sufficient in identifying fake data. However, it's obviously not the best, since it only does 80%. In the future, it would be beneficial to attempt to classify the data in live time. This would require creating a model which is able to detect the traffic directly as it enters the Sanren network. It would also be beneficial to Sanren if more attributes of the traffic, such as the number of failed logins, the error rate, etc., were collected, since the model will become more accurate in detecting fake traffic. Thank you.